today. We'll switch to English as we have some international guests. And Antonio Sollima is our speaker today. Antonio is a good old friend of ours, of the Observatory of Teramo, Abruzzo today. He's got his PhD in Bologna in 2006, working under the supervision of Francesco Ferraro on a thesis about stellar populations in Omega Centauri. And then he moved around for a few postdocs, Bologna again, then Tenerife in Spain, and Padua. And then since 2006, he's a full staff researcher at the IIS in Bologna again. And today he will talk about Gaia view of tidal tails of nearby globular clusters. So Antonio, please start. Let me recall you that you mute your microphone, and the questions we agreed that questions will come at the end of the presentation. And so Antonio, you have 45 minutes. I'll inform you 5 minutes ahead of your time.
Okay, thank you, Michele. Welcome, everybody. So today I will talk about some recent results I obtained analyzing Gaia DR2 data with the aim of detecting and studying the tidal tails around the sample of nearby globular clusters. So this is an animation where I show the process of mass loss in a stellar system. For instance, loss process is not isotropic, but stars are lost in particular directions, in particular forming tidal tails, which are located at opposite direction of the clusters, and which follows a very peculiar S shape with the central part which is inclined with respect to the outer part. And the outer part is aligned over the large scale with the cluster orbits, with also, if you look into the distribution of stars inside the tidal tails, you can see that also there are overdensities and underdensities. So the analysis of the tidal tails is important because you can obtain constraints on the cluster orbits, but also on the on the galactic potential and on the recent mass loss history of the system. So to understand how does it work, consider that any stellar system which is immersed within a tidal field feels the tidal strain of the host galaxy. And the stars feel so an effective potential, which is given by the sum of the internal potential, the external potential, and a term which depends on the motion of the cluster. And so this combination breaks the spherical symmetry, and you can see that in the left panel, for instance, is the Roche lobe, so the equipotential contours, which the cluster is contained. And you can see that there are two saddle points along the direction which links the cluster with the center of the potential, the external potential, so the galactic center. And in the right panel, instead, there is the projection of the effective potential along the three orthogonal directions. So the x direction is the one directed toward the galactic center. And here you can see that there is a maximum, a local maximum, which is located at a distance which is called the Jacobi radius, and corresponds to the distance of the first and the second Lagrange point of the potential. Then along the y direction, which is orthogonal to the x direction, but inside the orbital plane, the potential profile is the same of the cluster as it would be isolated. And along the z direction, which is perpendicular to the orbital plane, instead, the potential is a growing function of the distance. So this means that whatever is the energy of the star, there are no stars which can escape along the z direction, because there is always a wall of potential which stops the stars at a given distance. So there is a relation which links the potential and the density profiles, and this is the Poisson equation. So if you consider that the potential contours are distorted in a given direction, also the density contours are distorted in the same direction. So as I showed you, so there is an elongation of the Roche lobe toward the direction of the galactic center. So this means that Also, the density will be distorted in the, and this is the reason why in the inner part of the tails, the distribution of stars is elongated toward the direction of the galactic center. So this is just because stars take the shape of the Roche lobe. This is a three-dimensional view of the same process, where so you can see that if you choose the energy level given by the purple line, so you see that the structures is almost spherical, while if you increase the energy of the stars and you reach the energy level of the Lagrangian point, so you see that now two apertures appears surrounding the Lagrangian points, and so the stars which have this energy level can escape only through these two apertures. This is the reason why the mass loss is very anisotropic in the case of so mass loss from stellar system in tidal fields. And all the stars which exceeds this energy can escape. There are many reasons why this can occur. There are many channels of mass loss. I list just the three main channels. So the first occurs in the very early evolution of the cluster and is linked to the expulsion of the gas, the primordial gas from which the cluster form, or because of the mass loss driven by the stellar evolution. Because the supernova feedback, when they explode, they release an energy budget which is large enough to expel all the gas. So this produces a loss of potential energy before there is a significant exchange of kinetic energy. So the cluster, to maintain its virial equilibrium, must expand, and the potential well so decrease in depth. Decreasing in depth, what happens is that it brings up the energy of all the other stars. In this case, one says that the potential perform a mechanical work on the stars. And so these stars can exceed the energy of the Lagrangian point and can escape. Of course, here I showed you an exaggerated situation, but just to show that this process can be effective and works in the first 20, 30 mega years, more or less, of cluster evolution. And can be important in the case of globular cluster. For instance, if you consider the scenario formation of multiple population, where you expect that the first generation is lost immediately, and this is the process which is thought to be responsible for the loss, the efficient loss at early epochs of the first generation. Another way you can lose stars is through two-body relaxation, which is effective in all those stellar systems with enough mass relaxation time, which is shorter than the age. So this means that stars has enough time to interact between energy with the least massive stars, which gain kinetic energy, so start to climb on the potential well. And after many relaxation time, they can exceed the energy level of the Lagrangian point and escape. And this is an efficient method of mass loss. This is the main driver of mass loss, at least in relaxed stellar systems, so like globular clusters, open clusters. The last channel is through tidal shocks, occurring when the effective potential is subject to a sudden change over a time scale which is short, where short means shorter than the typical time scale of a single star to complete an orbit inside the cluster, so the dynamical time scale. When this occurs, there is an impulse of energy, which is whose amplitude is proportional to the square of the radius so from the cluster center. So this means that after the shock, you have an increase of energy, and the stars at large distances, so close to the tidal radius, can exceed the energy of the Lagrangian point and so be subject to evaporation. This can occur, for instance, when the cluster crosses the galactic disk, or when the cluster performs a pericentric passage. Okay, so once the stars escape, the Lagrangian point with a velocity which is directed orthogonal to the cluster velocity. So they became independent satellites of the galaxy, and so they feel this very complex acceleration, which is given by the sum of the internal acceleration, which now is felt like a point mass for the cluster, the tidal field, and then there are all the Euler pseudo forces, which in this order are the Coriolis force, the centrifugal force, and the Euler force. And so what dominates here is the Coriolis force, which is this one, and is directed in these directions. So on the two opposite sides of the cluster, this acceleration bend the stars parallel to the velocity vector, the systemic velocity of the cluster, but in two opposite directions. And this is responsible for the torsion of the tidal tails and the characteristic S shape. So with the central part oriented toward the galactic center because of the shape of the Roche lobe, and the external part, which aligned with the cluster orbits because of the Coriolis force. If you look at the distribution of stars inside the tidal tails, then you can see that there are also overdensities at regular position, at the regular distances from the cluster center, and these are due to the fact that these pseudo forces act on the escaped stars, accelerating and decelerating them periodically. So stars follow these epicyclic motions in which there are regions where they spend more time, and so there is an overdensity of stars. The distance of these maxima are a fixed number of times the Lagrangian radius. So this means that they depend on the orbital characteristics, like the orbital period, the eccentricity, the cluster mass. And this is true both for circular orbits and eccentric orbits. So in general, if you study the shape and the orientation and the characteristics of the tidal tails, so you can constrain the orbits of the cluster. And in some way, you can constrain, if you have many clusters, also the potential of the galaxy. Then, if you consider in a simulation, for instance, the distance of the stars along the tail versus the time when they escaped, you can see that beside a large scatter, there is also a very nice correlation. So this means that if you look at large distance from the cluster, you look back in time, and you can see the process of mass loss as it were many gigayears ago. This can be important because, for instance, if you want to study how was the loss of first generation, for instance, in globular cluster 3 gigayears ago, if you have a good view of the tidal tail at 10, 20 degrees, you can see this process at work back in time. So in general, this correlation means that you can use tidal tails or the fractional stars in the tails to study, to trace the recent mass loss history of the cluster. From an observational point of view, the detection of tidal tail is quite challenging. And I will show you in this simulation where I took an embodied simulation with characteristics typical of a normal globular cluster projected on the plane of the sky. Here you see the cluster and the tidal tails. The complication is that in practice, what you see is the superposition of the cluster with the field. And if you consider an homogeneous distribution of field stars, for instance, at these galactic coordinates, which are not that particularly critical for contamination, you see that now it is much more difficult to identify the tails. Also because you don't see the stars colored, but you see them in black and white. And so here it is difficult also to identify the cluster now. Of course, you can select stars. And in general, when you do this kind of analysis, you also have more than one filter. So you can compute a color-matrix diagram and select the stars along the main sequence, for instance, where you expect to find more cluster stars, more member stars. If you do this, for instance, of course, you reduce the contamination from the field, which, however, is still large enough to mask the location of the tidal tails. If you look at the past studies on tidal tails, you make a research in the literature, you realize that there is at least one paper for each nearby cluster claiming for the detection of tidal tails. I'm a bit critical with many of them, but that's because there is a strong problem, which is the fact that in many of these works, the analysis of the tails is made only on qualitative grounds. So usually people make a kind of photometric analysis, select the stars, or adopt a matched filter technique, derive a density map, and then compare 2 sigma or 3 sigma contours with the location of the tidal radius. And they see if there is a deformation of the contours close to the tidal radius, claiming if there is a tail. But there are many passages, many tasks, which are critical in this kind of job. For instance, one of them is the smoothing. This is, again, the same simulation. Before, you can see, now I assumed a smaller contamination. Here you can see the tidal tails clearly. And if you make, indeed, an optimal smoothing, you need a smoothing because you have a discrete distribution of stars, and you want to a density map, a continuous map. So you have to assume a kernel, for instance, or in other words, a bin in space. So if you make an optimal bin, you can make this kind of density contours where you see the tails clearly. But, for instance, if you do a bin size which is too small, then this is what happens. So you lose completely the tails. And this is because if the bin is too small, you start to see the granularity of the system. Or, in other words, you have a bin which is so small that you start to take 1 star per bin. And in this way, the region with an intrinsically low density falls below the Poisson noise. You can also have spurious detection in the other direction. For instance, if you have a simulation where there are no tails, but you use a bin size which is too large. So in this case, what you obtain is the convolution between the actual density and the kernel size. So you obtain a density contour which is too large, but this is spurious. It's just due to the fluctuation at the boundary of the cluster, and the fact that you have a convolution of the two distributions which exceed what you are assuming as to be the tidal radius. And indeed, if you make different extractions, so considering different clusters, you have different contours which at each time always exceed the distance of the tidal radius. But in this case, there are no. There is another point which regards the choice of the tidal radius. Because usually when you do this kind of study, you select the tidal radius. Many studies take the tidal radius listed in the ARIES catalog. However, this radius is calculated by fitting a static model, for instance, a King model, to the density profile. So this can be good to have an idea, a guess of the size of the cluster. But it is not the radius at which you can find all the bound stars. Because you can also have a cluster which is entirely contained within the Roche lobe. And so, for instance, this is the case of the top panel, the density profile, and the bottom panel, the potential, the effective potential profile. So there is a difference of a factor of 2, in this case, between the tidal radius and the Jacobi radius. And so this is important because when you look at tidal tails, you would like to look at all those stars which are unbound, while the stars that are contained between the tidal radius and the Jacobi radius are still bound to the cluster. There are, however, some cases in which there is an indisputable detection. So, for instance, this is the case of PAL 5, where you can see a beautiful tidal tail extending for more than 20 degrees with a direction of the tail aligned with the cluster orbits. Or, for instance, the case of NGC 5466, again, with the tails oriented in agreement with the orbit. And there are some few other cases in which there are this kind of clean detections. Can we use Gaia for this purpose? So, of course, Gaia have advantages and disadvantages. The main advantage is that you increase the dimensionality of the parameter space, because you don't have just the position, the color and magnitude, like in any photometric study, but you also have the motions and the parallaxes. So if you increase this dimensionality in all these multidimensional space, you can use the location of the stars to distinguish members from interlopers. So in this way, you increase the efficiency of reducing the noise. And also, besides this, you have there is the fact that you don't need to make a proposal, because Gaia provides information for all the globular cluster in both hemispheres for free. But there are also some clusters which are intrinsically faint, for which you cannot sample the entire population of the cluster, but with Gaia, you can reach a magnitude which is between 2 and 4 magnitude brighter than what you can obtain with canonical photometric analysis. So it depends, because if you use Gaia, you can reduce the noise. If you use a deep photometric analysis, you increase the signal. So there are cases or the other approach. This is, for instance, the simulation of before. And if I add, for instance, the selection, motion, and parallaxes, now you can see that the field contamination is reduced, even if also in this case it is anyway hard to detect the tidal tails. Since the second Gaia release of data release of Gaia, there were these 5 papers claiming tidal tails in nearby globular clusters, beside my paper, which analyzed instead a sample of 18 nearby globular clusters. So the globular clusters I selected were all located within 20 kiloparsec and at galactic latitude, which is higher than 5 degrees above the galactic plane, to reduce the extreme case of contamination. And I selected an area surrounding 5 degrees, in a radius of 5 degrees around the cluster center. And I retrieved, so, the Gaia catalog in all the 5 dimensions. And I adopted a technique which is called the 5D mixture modeling, which it is complex in the details, but quite simple in the principle. Because, for instance, consider just 2 parameters instead of 5, so A and B. So the location or the distribution of stars in a given portion of the space in this in the plane formed by these 2 parameters will be given by the superposition of the distribution of field stars and cluster stars, which can be seen as the combination of the normalized distribution of cluster and field stars with normalization factor of the density of globular cluster and density of the field. And this distribution is then convolved with observational errors. So what we are interested in is only this number, so the normalization factor of the cluster. To estimate it, so first I choose a parametric model for the cluster and for the field, whose parameter have been tuned to best fit the distribution of stars in this plane, accounting also for the observational errors. So when the normalized distribution are chosen, then a likelihood to each star has been assigned, a likelihood to be a cluster or a field stars, and then based on this likelihood, the relative fraction of globular clusters and field stars has been tuned to maximize the overall likelihood. And you can repeat it in many regions of the space, account for the distribution of the cluster and field stars. Of course, when you want to extend this formalism in 5 dimensions, taking into account for error, covariances, and whatever, it became a mess, but it is doable. And I did it, assuming, of course, different parametric model for the cluster and the field, which should be simple enough to be easily convolved with observational errors, but also complex enough to capture the overall distribution of the stars in this parameter space. So, for instance, for the globular cluster, a Dirac delta in parallax is enough, because you are not able to distinguish the individual depth of the stars along the line of sight, while for the field you have to use an empirical distribution which accounts for the distribution of parallaxes along the line of sight. A King model is enough for the cluster, while it is necessary to consider a multidimensional Gaussian expansion, also considering the different slices in parallaxes. And in the same way, for the collimated diagram, I consider the empirical distribution of stars, so the S diagram, considering that the cluster, you can derive the S diagram just in the observational plane. So apparent G magnitudes and intrinsic BP minus RP colors, while for the field, you have to consider that different slices in parallax have different collimated diagrams. So you have to use absolute magnitudes. From this, you can calculate the probability of cluster and field stars in the proper motion, parallax, and collimated diagram plane. You multiply all of them, and then you can derive the normalization by maximizing the overall likelihood. Okay, so if you do this, for instance, this is in the case, an example of NGC 1799, where you can see the ratio of the likelihood of field of a cluster versus field. So in red are to be cluster, and in blue, the largest probability to be field. So here you can see that this method works and properly select the member stars. You can see the largest likelihood is, for instance, for the horizontal branch stars or turn-off stars, where there is the maximum contrast, and then also around the mean parallax of the system and mean proper motion. And even just considering only the location stars with largest likelihood, you can see that also in the space you can also guess already the location of the tidal tails. Then the next step is to define a criterion to claim a tidal tail. So I adopted two different criteria, which must be both satisfied, which are linked to the definition of tidal tails. So you can define tidal tails as an extratidal overdensity of stars above the background emerging from both sides of the cluster. So following this definition, I define first a criterion in which the 3 sigma closed contours containing the cluster center must exceed the Jacobi radius, not the tidal radius. And in this case, the Jacobi radius has been calculated using the orbital motion of the cluster, the systemic motion derived with the Gaia proper motion and the literature radial velocity, and a galactic model. And the second criterion is that there is an alignment of the tails. So for this purpose, I defined these two opposite sectors, and I calculated the integrated density inside this area and outside the area. And in the bottom panel, there is the ratio of these two densities, which can be at different position angles. So there is a position angle in which there is a maximum, and you can calculate using a Monte Carlo technique what is the fluctuation, which is linked to the Poisson noise. So the second criterion is satisfied when there is a maximum which exceeds 3 sigma. Okay, so now we have a quantitative criterion to define tidal tails. So applying it the sample of I analyzed, so I can now show you the results. So there are some cases with positive detection. This is, for instance, omega sen, where now you can see very clear tidal tails, which extend and cover the entire area, which have been analyzed here. So here you can see that there is in dashed line the direction of the galactic center, and the solid line instead is the calculated orbits. Here you can see that there is the location of the tidal tails is oriented in between these two directions. And these detections agrees with the one which have been showed just a few months before by Ibata et al. Using the same Gaia datasets. This is the common area. You can see that there is a quite good agreement, even if they analyze a larger area. And this for omega cent is quite important because there was a long discussion if this cluster hosts or not the tidal tails. So now we can say that yes, it hosts significant tidal tails. This is another case, NGC 288, where again you can see the leading arm of the tidal tails at 3 sigma above the background. And also here is interesting to see that there is a torsion of the tail, because the central part of the tail is oriented in a different direction with respect to the external part. So in agreement with what I told you before, of the variation of the angle with the distance. And this is also agrees with the recent analysis of Kader Ali et al. 2019, even if, in my opinion, my density contours are a bit cleaner. Another case is NGC 6341, for instance. Again, in this case, you can see the trailing arm of the tail, very well defined and also well aligned with orbits of the cluster. This means that also the orbits is well calculated, and at least the potential in this region of the halo is well constrained. And this also agrees with a recent paper which has been made by Thomas et al. Using DECAM data, which are 4 magnitude deeper than the Gaia data. So this means that the advantage of using Gaia data is significant in this case, because you can detect the same tidal tails in a way which is as clean as what you can obtain with photometric data 4 magnitude deeper. There are also clusters in which there were no previous detection of tidal tails. So for instance, NGC 2298 is one of these cases. And here again, you can see very well-defined tidal tails on both sides of the cluster, aligned with the cluster orbit. And then the masterpiece, which is NGC 7099, where you can see now a wonderful detection of tidal tails, which extend over the whole field of view analyzed, so 10 degrees in diameter, with 3 sigma contours and also 5 sigma contours up to the boundary of the analyzed field of view. And also you can see now the S shape of the cluster, with the inner part aligned with the direction of the galactic center, and the outer part, which resemble the direction of the orbits. This is a family picture, the 9 of this cluster. So globally, I found detection, significant detection on 6 clusters, plus a 2 sigma detection, so which means that I find one of the 2 criteria satisfied at 3 sigma and the other at 2 sigma for 2 clusters. So here you see there are in red the cluster with significant detection, which are all contained among those I showed you before. The 2 sigma detection is NGC 3201 in this case, where you can see there is a small deformation of the contours at 3 sigma, which is aligned with the direction of the galactic center, but still not very collimated in one direction. There are also other cases in which you have some overdensities outside the tidal radius, but not that significant. And these are the other clusters, and the significant detection are also indicated in red. There are also significant detection in NGC 5904 and NGC 6362. However, for these cases, while the detection is significant, however, the extension of the tidal is large enough to perform further studies. There is also 2 sigma detection in NGC 6752. So what kind of study can we do with these tails? So one is to check if these tidal tails are actually aligned with the orbits. So this is the orientation of the tails at various distances from the center. And you can see the dashed line is the direction of the position angle of the galactic center. And in red and blue are the position angle of the leading and the trailing, according to the orbits I calculated. So individually, you can see that the errors are quite large. So if you apply a chi-square test to any individual cluster, all the results are not significant. Even if there are some cases in which there is a clear transition, like for instance, NGC 288, you see that the inner part is close to the dashed line, so the galactic center, and then there is a clear transition at large radii toward the orbital direction. Also other cases, NGC 1799 again. If you consider, however, all the cluster together, and you apply a chi-square test to all the clusters together, then the probability that the agreement with the direction of the orbits occurs by chance is smaller than 0.2%. So I can say that there is a 3 sigma significance of the alignments of the tidal tails with the orbit directions. So in agreement with what you expect from the dynamics of the stellar system, these stellar systems. Another thing which can be done is to constrain the rate of mass loss. You can see here in the left panel the observational density map of NGC 1799, for instance, and in the right panel there is an n-body simulation which have been run assuming a given mass loss rate. So you can see that the stars are distributed more or less in similar ways, so you can define 2 regions, one encompassing the 2 tidal tails, and one containing the cluster center. So you can calculate in both cases the ratio of the integrated density of the 2 regions, or in the other case, the ratio of the number counts. And if you change, you perform many simulations, assuming different mass loss rates, you can find the value which best match this ratio. And this provides a semi-empirical destruction rate, which is the only way you can derive an empirical value measure of this quantity. Because the only way to estimate the destruction rates otherwise is only theoretical. So you can run an n-body simulation where you assume the cluster has a given mass and the potential has a given shape, and then run it and see how many stars are lost. So some other studies in which there are some analytical formula or approximation which are adopted. But this is the first way you can derive an empirical value, based also constrained by observations. And this value can be used to test the other models. For instance, in this case, you can see the comparison between the derived mass loss rate with those derived by the simulation of Striker, Allen, and Baumgart. So you can see that, for instance, for Striker and Baumgart, there is a good agreement, while for the simulation of Allen, there is a mismatch, a significant mismatch. So this is a good way to test these n-body simulations. The other, and probably the most important, the most interesting application of scientific application of the detection of tidal tails is to constrain the galactic potential. Here you can see, for instance, for the 5 clusters, for significant detection of tails extending over a wide area, is compared with the prediction of the orbits in the case of 2 different galactic halo mass. And here you see that within the limited area I considered, there is no space to make a distinction between these 2 masses. But for some cluster, for instance, NGC 1799, just beyond this radius, you can start to see some difference. So, of course, the project I did now was just a pilot project where I analyzed many clusters on a restricted area. But of course, it is possible to follow up in which one can analyze only for these clusters, of course, a wider area, both using Gaia Tier 2 or Tier 3 better, but also, for instance, one can do other follow-ups with some photometric follow-ups or spectroscopic follow-up to constrain also the radial velocities. And this could be useful because in this case, one could be able to constrain the galactic potential, taking advantage of the fact that you observe many clusters in many different directions and location inside the halo. So you can constrain not just the mass of the halo, but also the flattening of the halo, for instance. So, summarizing, in this study, I searched tidal tails in a sample of nearby globular clusters, and I found significant detection in 6 globular clusters plus 2 globular clusters with 2 sigma detection. The detected tidal tails are always aligned with the cluster orbits, and this agrees with the prediction of dynamical models. And I use these tidal tails detection to constrain the reasoned mass loss rate from this tidal system. And this constitutes the first observed estimates of the mass loss rate in these systems, which are being compared and used to test the n-body models. The perspective of this kind of study are, of course, to make follow-up observations of the cluster with a positive detection. So here one could think to, for instance, to study the most distant cluster using deep photometric data to reach the main sequence, where you have so much more information because you have much more contrast with respect to the cluster interlopers, or for instance, to use radial velocity data to, of course, only for the brightest stars in this case, but to also constrains also the streaming motion of the tails in the radial directions. And also it's possible to do the same with the next release of Gaia. Of course, the aim is also to use these tidal tails to constrain the shape of the galactic dark matter halo potential. And the good news is that this can be done with increased efficiency in the next future, because from the next release of Gaia, which is expected in December, the uncertainties, the covariances, and the inhomogeneities are expected to be greatly reduced. And this is crucial in some cases, because, for instance, even in the second data release, for instance, the limiting magnitude is a function of the position because of the Gaia scanning law. So you can have some spurious pattern which force you to adopt a brighter magnitude cut, so reducing even more the number of stars you can properly use for this purpose. So if you reduce this effect, you can increase the efficiency in detecting tidal tails. Okay, finish it. Thank you.
So thank you, Antonio. Very nice talk and very nice work. Now we are. Oh, you've been very precise in time. And also, if we have questions, this is the right time to ask Antonio.
I have one, if I can.
Yes.